One day, a couple of years ago, I was doing some research on YouTube when I came across this channel from Ben Eater, and it took me back to my roots of when I started developing software back in the late 70s. It made me feel kind of nostalgic for the old days. My first computer was a Heathkit H8 computer, which was paired with an H9 terminal, also from Heathkit. The Heathkit H8 computer was based on the Intel processor. The first computer language I learned was the Intel command set. In those days, coding meant manually entering in hex codes through the front panel switches of the H8. As time went on, Heathkit introduced HDOS, the Heathkit disk operating system, and we could then use assembler and editors. That's when I started ABS Data Systems, a custom software development company. Now back to Ben Eater's channel. Since I never coded on the 6502 microprocessor, and that Ben offered a kit for sale, I decided to pursue the 6502 computer and purchase one of his kits. Like any project, it takes time to learn and build. My frustration came quickly. You see, I never worked with the 6502 and its assembler, and I made a lot of mistakes. Nowadays, I work in C++ or C#, which are languages that perform a lot of checks for you. So the process of taking the EEPROM in and out several times, or what seemed like thousands of times, wasn't going to work for me. I then realized that others might be frustrated doing the same thing. Today, I think we relied on technology too much and have forgotten all about the basics. I think it's important to understand how things work. That's why I started the 6502 project. I started this project a couple of years ago, was able to get the boards designed and built and partially tested and coded. Since the inception of this project, I retired, which allows me to spend more time on my hobbies. The 6502 project is the first project I plan on recording. I'm sure other projects will follow. For now, the 6502 project is a series of videos which will outline the design goals for this project, from design concepts, implementation, trade-offs, and the reasons why I made certain decisions. I'll run experiments to verify that the hardware and software work as designed. My plan is to document not only the successes, but the failures in hopes that others will learn from the process rather than the solution. My biggest strength has always been troubleshooting and debugging issues. That's the real lesson you'll learn from my channel. Now let's get started on the 6502 project design goals. The initial design goals of the 6502 project were simple. Take Ben Eater's original design of the 6502 microcomputer with its 32K of RAM and 32K of ROM, and have the ability to program the EEPROM without removing it from the circuit. What you're going to find out about me as you watch my videos is that that's not how I think. You see, I over-engineer everything. Why? That's simple. My mind races. The more I think about a project, the more uses I find for using it. You'll see this as the project design unfolds. I've worked with a number of electrical engineers over the years. They are focused on solving the problem right in front of them. Then later, a new idea appears, and we're back redesigning the same board with a few additional components. And now we have two versions of basically the same board. The design phase is when you should take a step back and ask the real question: is this how I want to use this in the future? As of today, I can't fully answer that question. So let's add the features that I might want. As I look back to the beginning of my computer experiences, I always said that I wish the engineers had added this feature, or I wish they had added that feature. I want more expansion. Well, it's my turn, so let's add it. Developing software is way more flexible. If you don't like what you've designed, just recode it, recompile it, load it, test it, repeat the process until you get the desired results. Designing hardware is expensive. Originally, my thought process was to add a couple circuits to the CPU board. This was forcing me to make decisions like one serial port or two digital outs or two digital ins. As you can see from the list, just keeps growing and expanding. I'm now designing an ESP32 with a limited feature set, but that's not my overall goal. Here's my updated goal. I want to take a modular approach, create a series of modules that I can add into the system, which will alter the overall functionality. Each board should have its own microprocessor so it can run independently. This provides me with more processing power, localized buffer. Using the same hardware, I can customize code to even get more flexibility out of the same set of hardware. This is really important. A modular approach solves the issues of not having enough I/O. Since each module has its own, in most cases, 8 ports, if I wanted 12, I could just use 2 modules. Now that I've settled on the multiple modular approach, it's time to redesign the original 6502 microcomputer. Now the real journey begins. Let's start on the CPU board design. Before I get into the design specifics for the 6502 CPU board, I wanted to review with you the bigger picture of what I was thinking about. Originally, I was planning on designing a Z80 computer using the EZ80 F91 chip from Zilog. I made this decision because I found the source code for MS-DOS on GitHub. This is the second operating system I learned. The first was HDOS, Heathkit Disk Operating System. It only seems logical to use MS-DOS since the source code is available, which will be a big time saver. All I need to do is to modify the source code to match my hardware design. While researching the Z80 project, I came across Ben Eater's channel and added the 6502 computer to my list of designs. Currently, the design of the overall system is that the 6502 will act as an intelligent peripheral controller to the Z80 computer. While designing all the support modules, I have changed the design to be more modular in approach, being that the Z80 or the 6502 can share the same module base. My thought process continued to develop, and I thought that I should not re-engineer the peripheral interface twice, one for each of the CPU boards. I added hardware to support this approach on the 6502 computer as a peripheral to the Z80. However, the 6502 computer will be designed as a standalone computer. The Z80 interface is the same basic interface as with the other modules, and in fact, think of it as a 13th expansion port. Furthermore, this port could be used for anything. For now, this series is about the designing of a 6502 computer. Since I started off with Ben Eater's diagram, there were several areas I wanted to improve on. CPU performance from 1 to 14 MHz. Increase program storage capacity from 32K to 512K. Advanced debugging with the use of LCD display modules and LEDs. Onboard programming and JTAG-like functionality. An expansion bus so that I can attach 12 modules. Granular control logic to limited wasted RAM for module interfaces. And AVR smart buffers. How do I plan on using the 512K of EEPROM? My intent behind increasing the ROM storage from 32K to 512K is so I can have multiple programs stored in a single ROM. That way I can swap in and out different functionality without having to reprogram the device. Technically, there are several things that are involved in this concept. A page register, and I need to map out the ROM for paging. All the compilers I've looked at so far do not have this feature. There's a workaround for this. We can use common fixed memory locations for all the code that needs to be shared across the pages. That way it can be handled in the compiler or code settings. Each code base would need to use the same mapping as part of their project or code base. Since I've written my own programmer, it will be up to me to read and program the correct pages in EEPROM. Another design goal is to reduce the interrupt service routine. The modules themselves have their own processor. My thought is to create an ISR where the data can be bulk transferred from the module directly into the CPU memory buffer. This will allow me to write an ISR in bulk transfer style, not sending a character at a time. I added a CPLD. A CPLD, which stands for Complex Programmable Logic Device, is a programmable logic part that will allow me to, based on the inputs, control the outputs. Think of this as software designing hardware. This is the glue logic for the entire CPU board. The way this part works is that you write code in a text editor, compile it, and test it in a simulator, then upload it into the part. I will create a separate video on how to design and test CPLD code. On the block diagram, I mentioned AVR several times. This refers to the microchip AVR64DD32 part. It's a very nice low-cost part that can operate up to 24 MHz. It has its own internal oscillator and 27 I/O pins. It also has 64K of flash and 8K of RAM. I think I pay under $1.50 for this part, and this chip is more powerful than my first computer. This is the same part I used in all the modules. Think about this concept. If one of my biggest concerns in the past is the number of times you enter an interrupt service routine to move data, being 1 or 2 characters at a time, then the concept of bulk data transfer now makes more sense. Because this device is a computer, if I detect bottlenecks in the interrupt service routine, I can adjust the buffer levels of each module to fine-tune performance on any of the peripherals. An important note. Just because I designed a feature on the CPU board or on any module doesn't mean we need to populate the parts. Remember, hardware is fixed and costly to design. It's better for me to think about and add the expansion now than to wish I had done so later.